This is WFNP 88.7 Rosendale. Welcome to Curiosities of the Cosmos. I'm your host, Allyson Sheneman. Today I've brought on Phoebe Heretz to talk about astrophysics and the universe.
Welcome to Curiosities of the Cosmos with Allyson Sheneman. My guest today is Phoebe Heretz. Phoebe is a student at SUNY New Paltz in astronomy and physics. She is a returning student who originally studied music at SUNY Purchase, and she's a passionate science communicator who is also a planetarium presenter on campus and a NASA JPL Solar System ambassador. She is an astrophysics researcher studying galaxy evolution and protoplanetary disks and is excited to begin a PhD in astrophysics in the fall. Phoebe, thank you for coming on the show today.
Thank you, Allyson. I'm very excited to be here.
I'm very excited to have you. For our listeners, Phoebe and I both started in astronomy at the same time and place in undergrad, and we both present at our campus planetarium. It has been an incredible honor and privilege to watch her grow and truly excel in the field, to earn so many incredible positions, research projects, awards. It's wonderful to have you on, and thank you for taking the time to be here.
I could say the same thing about you, Allyson. Thank you.
Of course. So we're going to first start the show by talking a little bit about, as I mentioned in your introduction, having started in music and then kind of transferred into astronomy and physics. It feels like a change people don't probably expect from somebody who's studying music. Can you talk a little bit about like what drew you to astrophysics and maybe what pushed you away from music?
Sure, of course. So I feel like both astronomy and music have been some of my biggest loves in life since I was a kid. I definitely fell hard for space and the universe when I was about 10. I will say I nerded out about Carl Sagan's Cosmos and Contact, a 90s movie, which is still my favorite movie.
Yeah.
Around that age, and I felt sure about becoming an astrophysicist at that time. But I went to a pretty rigorous high school, which I am grateful for now. I received an incredible education there, but it wasn't the right time in a lot of ways because I was a teenager, going through teenage years, a lot of struggles, and I relied on music and expressing myself creatively at that time, and kind of I turned away from the academic pressure that was weighing heavily on us in high school. And so that's why at that time I decided that pursuing songwriting was the right path. And it was. I had a wonderful time at SUNY Purchase. I studied the studio composition, which it's one of the only programs in the country that will teach you songwriting. And I had a wonderful time. I just came into my own. I had a great social life there and wrote a lot of songs, performed a lot, kind of became a more confident performer. So I had a wonderful time there. But then, then real life hits, and I graduated, and then all this pressure was on music to pursue it in the hopes of earning money. And that totally just snuffed my creativity pretty quickly. I moved to New York City, which was the next logical step from there, and just like face planted for like a whole year, just really struggling. And so I felt like my creativity was snuffed, and I had to figure out a way to make money, essentially, as an adult. So I kind of landed in database work, which is kind of random. But that work actually re-triggered my love of science and math. Like, just the same parts of my brain fired again. And I really missed it. I really missed how much I loved science and math growing up. And I was laid off from my full-time job right when the pandemic hit. it was actually right before the pandemic hit. It wasn't even related to the pandemic, just the company I was working for had a restructure.
Unfortunate timing.
Very unfortunate timing.
Yeah.
And so everything with the pandemic, everything was thrown up into the air. We didn't know what was going to happen. And I was rewatching Carl Sagan's Cosmos and just like cried my eyes out the whole entire episode. And I felt like I was hit like a train. I was like, why don't I do it? Why don't I go back to school for astrophysics?
Yeah.
And of course, the music degree didn't have a lot of overlap with an astrophysics degree, so I went back for a full bachelor's, and it's almost done. It's 4 years have gone by already. It's wild. And I was accepted into PhD programs, so the path
Congratulations.
is here. Thank you.
Yeah.
It's felt pretty meant to be this whole time, so I'm very glad that I made the decision. And music is still a part of my life.
Yeah.
I feel like, unfortunately, I was never able to recover the creativity as much as I would have liked to. With the pressures of adult life, it gets harder. That when there's stress around, it gets harder to carve out time to be quiet and to be creative.
Yeah.
But I think you asked about the overlap between music and science.
Yes, yeah.
And I really like that. And I feel like people don't expect a lot of the times that there is an overlap between music and science. But I totally think there is.
Yeah.
So I grew up really loving math and the patterns and the structures that come with the language of math. But it's the same thing with music.
Yeah.
And that's my favorite part about music is like all these beautiful patterns and just like built-in language of music.
Yeah.
But then also forming these, like a great song has really like intricate, beautiful patterns and structures to it. So that was my favorite part about writing songs was it wasn't necessarily like writing words, writing prose, but just like making those beautiful little music structures.
Yeah. No, I totally relate to that. I think I didn't have as comprehensive of a background in music, but I spent all of high school being very engaged in music. I was a part of like jazz band and marching band and concert band, and I played for our like pit for musical theater, and I taught guitar at an after-school center. And so it was really teaching it for me that showed me how many patterns there were, because I had to take the information that I knew playing like lead like jazz guitar and turn it into information that I mean anywhere from a 4th through 8th grader could understand and replicate. And so it taught me a lot about how to find those patterns, and it made music make more sense to me. And so to me, I feel the same way, that especially math, but science as well, is completely inseparable to me from music and art and being creative.
Mm-hmm.
Like I feel like you can't have one without the other, at least
Totally.
not in the way that they are like so beautiful and like
Mhm.
full, if that makes sense.
Mm-hmm.
Yeah.
And I also like, especially with the science of astrophysics, you know, it's the study of our universe, and that's already very existential and beautiful. And so I feel like art is just a natural way to express our awe of the universe as well as the pursuit of the science behind it.
Totally, yeah. And I think kind of like what you were just saying, it's like I feel like you and I have the same sense of like science that I wish I saw more in the public. And I think I see the most in the public when I talk about astronomy specifically. Because I don't know about you, but like when I talk about biology with people, or if I were to talk about physics with people, I feel like I don't typically start those conversations expecting that the person is going to be really excited about it.
Unfortunately.
Yeah, unfortunately, exactly. And I feel like for the majority of people, it's easy to do that with astronomy. But I think one way that I feel like I really relate to your experience in the field is that like we both have this sense of that kind of like awe and wonder and love of science across disciplines, and even the disciplines that are maybe like to the public harder to love, if that makes any sense. But yeah, I love like nerding out about science in that way. And I feel like sometimes music is, like you were saying, it's like an easy language to like express yourself in and really like, I don't know, like synthesize all of this information or these like stories that you want to tell, and you can do it in a way that is more accessible to people because it's in song. And so I feel like, I don't know much about it, and I don't know if you would know more, but I do feel like in our generation, there's been a push to do more like science songs, if that makes any sense. Like I know a lot of people who like memorize the periodic table in song, things like that. So I guess maybe there is more of an explicit way that they're being combined.
Yeah, it's interesting. So we are both science communicators. That's important to both of us. And I've thought about communicating science with music. I haven't gotten very far, honestly. But overall, my experience as a musician has made me a stronger science communicator, just in my ability to communicate and be a presence in front of people and not be shy. I used to be really shy, so I felt like if I had started working at the planetarium how I was as an 18-year-old, I would have been really shy and probably wouldn't have done it very well. So I felt like my experience as a performer gave me a leg up with science communication. But I haven't written any songs about science specifically, but I have written about nature. That's one of my favorite things to write about. So yeah, it is important to me. I had another thought too. I don't remember what it was, but I think I was going to talk about how you mentioned astronomy. What I love about it too is that it inspires awe in us, but it is also kind of the combination of like a lot of wonders of nature, like geology and biology and physics and chemistry, like all of the things that we are inspired to pursue in science are kind of all combined into one in astronomy. So that's another thing that I love about it.
Yeah, I think that is what drew me to it specifically. I was definitely one of those people that started in astronomy being fooled about like how much math and physics there was actually going to be. In pursuing astronomy and biology both, I was just kind of like, oh, I get to do the cool like space part of biology. And then I took a bunch of physics classes and I was like, that's not exactly how that works. They're all connected. And in doing biology, you can't not do chemistry. And the same goes for, I think, all sciences. But astronomy especially, I feel like, just has a way of combining everything and keeping it beautiful. Yeah, it's awesome. We're actually going to do our first segment of the show. So we have a segment called Should We Be More Worried About?
Excellent.
So from years of public science communication, as I'm sure you probably can relate to, you get asked a lot of questions, and a lot of questions that people might have because they just learned about a thing and or maybe they don't fully understand it. And so therefore they get nervous about like whether it's a bigger deal than maybe it actually is, or people maybe don't know about a thing that that they maybe should be more worried about. So Phoebe, should we be more worried about the expansion of the universe? Because it's accelerating. Is it going to pull everything apart? Is it going to pull the Earth apart? When is this happening?
That's a good question, Allyson. So, yes, the universe is expanding, and it's accelerating in its expansion, which is still one of the biggest mysteries of our universe, is what is pushing that acceleration of the universe. So, okay. We as humans on this earth should not be actively worried about the universe accelerating and expanding and accelerating, because it won't pull apart objects as relatively small as the Earth or even our Milky Way galaxy. So we physically won't be impacted by this expansion, which is actively happening right now, but we're here. We can't feel it. We can't sense it. So in that way, we don't have to worry about it. But there is kind of a bigger existential crisis involved with the expansion of the universe, and that is we think it's going to expand forever. We don't think, based off of our current understanding of the universe, that it's going to stop or that it's going to collapse. We just think it's going to keep on flying or stretching and expanding forever. And so that gets a little worrisome when you think about billions and billions of years from now. Again, something that we don't have to worry about in probably the time frame of even humans.
Yeah.
Eventually, what's going to happen, though, is there won't be enough gas left over for star formation in our galaxy. So all the stars in our galaxy will die out, and it'll be a dark place, our own galaxy. But then what's even weirder is, at that point, our galaxy will be so far apart from any other galaxy that just everything will look dark and like a void. So that's a little sad.
Yeah.
But you can think about it too, that we are actually in this like beautiful prime time in the universe.
Yeah.
Like, it's this wonderful time when things still are bright and light, and you can think of humans coming online, and now we can try to understand and learn about where we are, why we are. Like, we hear, like, we learned this in class last semester, like, we hear, we can think of it as the universe finally being aware of itself now that humans are here and exploring it.
Yeah.
So in that way, it makes me grateful to be alive at this time.
Yeah.
Before the great dark.
Yeah.
But again, don't have to worry about that for billions and billions of years.
Yeah. Not human timescales.
Not human timescales.
Yeah. No, it definitely makes you think on such a different like level, I feel. Because I think a lot of people shy away from astronomy and space because it can get so
big.
scary. Yeah, too big. Exactly. It's like trying to think on timescales that are outside of like human timescales is really hard because we've never had to do that.
Mm-hmm.
And we probably never will, hence why
Mm-hmm.
they're human timescales. So I think it definitely makes it, I like the use of the word existential, because it's hard to know what that would look like because we're not going to be around to perceive it anyway, really.
Mm-hmm.
And that's a whole other can of worms of fears and, and things to be worried about. So actually, we're going to take our first break right there. So stay tuned and we'll be right back. All right, welcome back to WFNP 88.7 The Edge, Rosendale. This is continuing with Curiosities of the Cosmos. I'm your host, Allyson Sheneman, and I am joined by Phoebe Heretz, a senior and student of astronomy and physics at SUNY New Paltz. We just had a great conversation about music and science and also the expanding universe, and we're going to continue now with more on astrophysics and the universe. So I'd love to discuss more about the research that you've conducted. So I know you've conducted a handful of different projects, so you can choose to kind of cover all of them or whichever one you're feeling most inclined to talk about. But could you explain your research as though I was like 5 years old?
Sure.
Yeah.
I guess I'm interested in talking a little bit about my whole experience with research, because I think it's helpful for other people who are interested in pursuing astrophysics to hear about how I got there.
Yeah.
Especially coming from music and being at SUNY New Paltz, which has a small astronomy department, and we don't have active researchers here.
Yeah.
So I kind of had to carve out my path to research a little bit. So I would like to share that with anyone.
That narrative
in the
is
audience.
so important and special. So yeah, absolutely.
So I came to SUNY New Paltz feeling very intentional about wanting to be a scientist pursuing astrophysics. And I knew that to do that, you have to be a researcher. That's how you actively do science, is by doing research. So when I came to SUNY New Paltz, I sought out research opportunities as soon as I could, and that involved, in my freshman year, before I had even taken a physics class, I had a small research position on Dr. Catherine Hearn's optics team.
Yeah.
And so that was a really cool experience. I was pretty much more of a fly on the wall, helping seniors set up the optics table with all of the cool optics components and the lasers, and they're working on calcite crystals being suspended in an optical tweezer. So it was all very exciting and really cool project, but I hadn't taken physics, so I didn't really know what was going on, but it was my first experience, and I was like, great, I like this, let's keep going. And so at that time, I was learning how to use our observatory in our observational class. So by the following fall, I was ready to conduct an independent project at the observatory. And I was able to take my own images of what we call Cepheid variable stars. And those are stars that they periodically range in brightness at a very regular period. And so they're very important actually in our understanding of the universe, because they're what allow us to understand the distances within our own galaxy and other galaxies. So they're like this great, what we call a standard candle that allow us to measure distances. So I was excited that at our observatory, I could take images across the whole entire fall of a few of these Cepheid variable stars, and could measure the periodic dimming and brightening of these stars over the course of a few months. So that was a really rewarding project, because I went out in the cold on clear nights, which, you know, is hard in New Paltz sometimes.
Yes.
And collected my images, analyzed my data, and then the reward was a result that matched what is currently known about Cepheid variable stars. So that was a rewarding experience. And from there, I felt like not necessarily exhausted, but I wanted the opportunities here at New Paltz for astronomy research. But I felt like once I had used the observatory, I was like, okay, now I want to look elsewhere for people that are actively researching astrophysics and see if I can join one of their teams. So I applied to what are called RUs, Research Experiences for Undergraduates in Astronomy. And there's like a few dozen of them in astronomy in America. So I applied to about a dozen of them. And I heard back from a professor at Vassar College. Her name is Dr. Colette Salick. And she studies what are called protoplanetary disks, which you can think of as baby solar systems. And what was so exciting about this research opportunity was she and her team of global protoplanetary disk researchers were preparing for some of the first James Webb Space Telescope data, which arguably, now we have 2 years of JWST data now, but it's arguably the best telescope ever.
Yeah.
So it was so exciting to be on the front lines of the launch of JWST and doing some really cool research for them as well. And then that experience brought me to a couple conferences, and that's an important part of being a researcher, is sharing your research with others, both other scientists as well as the public. Like, you want what you're doing to be engaging across a wide range of audiences. So that was a helpful experience to learn how to communicate with fellow scientists. And then the following year, I applied to REU programs again, and I was accepted to the SAO REU at the Center for Astrophysics, Harvard and Smithsonian, which was awesome. It was in Cambridge, Massachusetts. And that was another, like, huge, like, this is all meant to be moment, because when I got the call from the director of the program on March 1st, I'll never forget it, he told me that I was going to be working on galaxies and doing spectroscopy, which are two things that I really love, and they were going to be combined into one, and it was an incredible opportunity. And I guess I should explain what spectroscopy is a little bit for our listeners. I almost wore Jeremy, my fiance, he got me Spectrum earrings a couple months ago, so I should have worn them today, but it's okay. It's a radio show, so people can't see them anyways. So anyways, spectroscopy is one of, in my opinion, the coolest tools we have in an astronomer's toolbox. And what it is in astronomy, we only have the light coming at us from places in the universe. That's the only way we can do science in astronomy, is just from the light coming at us, because it's too far away for us to go out to another star, to another galaxy. The distances are just too large, so all we can do is study the light coming to us. And we've developed this science of spectroscopy, which essentially it breaks out the light coming to us from an object, whether it be a star, a galaxy, a protoplanetary disk. It breaks that light out into all of its component colors, or what we call wavelengths. So you can think about, it's the same thing that a prism does. When light passes through a prism and you see the rainbow on the wall, that's the exact same thing. That's what we call a spectrum. But you can do so much cool science with just a single spectrum from a galaxy or a protoplanetary disk. You can figure out what it's made of, the actual chemistry that is present in those places. You can figure out how those things are moving. Are they moving away from you? Are they spinning? You can figure out the conditions in those places. Are they hot? Are they cold? So there's just this like wonderfully complex amount of information in this one spectrum. So I'm a total nerd about it and I love it a lot. So when I was told that I was going to both be working on spectroscopy and galaxies, which I knew my heart was in, and now is what I would like to pursue, I was like, this is totally meant to be. This is like still one of the best days of my life, getting that phone call. So yeah, I spent the summer at Harvard. I got to live in the dorms, which was cool. It's like, if you've ever been to Cambridge, it's really beautiful there. There's like a lot of brick streets, and it's really beautiful. And the Center for Astrophysics itself has hundreds of scientists there, all working in one building. And so just like going to coffee hour, you know, I would talk to a scientist trying to find planet X or planet 10, you know.
Yes.
Have you heard this?
Yes.
Like a planet that perhaps is like tugging on stuff like way beyond Pluto.
Yeah.
Like amazing stuff like that. So it was wonderful to be there. And specifically what my project is so we're using spectroscopy to try to understand the chemical richness of galaxies. So in astronomical terms, we consider anything a metal, a quote-unquote metal, if it's heavier than hydrogen and helium, because those two elements, the lightest elements on the periodic table, were known to be created by the Big Bang when the universe formed, but all of the other elements on the periodic table, every single one of them, was fused in stellar processes. So when stars live, they fuse the heavier elements like carbon and oxygen and iron. But when they die, there's so much pressure and force when heavier stars collapse on themselves that they fuse the rest of the periodic table.
It's crazy.
It's crazy. So that's why people, when they say we're star stuff, that's what that means. Like everything in the studio right now, the table, the chair, us, our clothes, that's all from stars. All that material comes from stars.
Yeah.
So anyways, I'm getting too excited about too many things right now. So my research was trying to understand how much of this stuff is in galaxies as a whole. And so why this is interesting is because this heavier stuff is made from stars, you can assume that as more generations of stars live and die, you can assume that there's more stuff around. So, or what we call higher metallicity. So we're looking for a new way to measure the amount or how much metallicity is in galaxies across the whole age of the universe. And so that'll be another tool in our toolbox of understanding how galaxies evolve over the whole age of the universe. So it was an awesome, awesome project, and I'm still working on it, and I hope to keep working on something similar in graduate school.
It's awesome. I feel like I'm so glad you told it as a part of that like narrative of how you went from one thing to another and how it all builds on itself, because I think sometimes people just see somebody who's accomplished in a field and see it kind of in isolation from the little steps that it takes to get there sometimes. And so I think it's really cool for people who also might be interested in pursuing science and they're not really sure what it looks like to go from perhaps a rigorous academic background in high school to trying to figure out what it looks like for like a day in the life of somebody who's doing astrophysics research at Harvard. And so I think it's great to have that like picture painted of the in-between part, because sometimes we just see like the start and the finish line and none of the work in the middle that it takes to get there.
Totally.
But yeah. So thank you for that. We're now going to do another segment. This is
awesome.
Our Curiosity Corner. So in Curiosity Corner, I tell you a fun fact, and you rate how mind-blowing they are on a scale of 0 to 10.
0 to 10. Okay.
Where 0 is it's not fun or you already knew it. More probably that you already knew it, because I think we both find all fun facts fun. So it's kind of like whatever. And then a 10 is like you're going to think about it every day for the rest of your life, whether that's a good or a bad thing. So these are hand selected for you. I think these are things that you're going to find very interesting. So our first fun fact. There are more bacterial cells in your body than human cells. The average human is about 56% bacteria.
Ew.
Yeah.
That's nasty.
If it makes you feel any better, because bacteria are so light, by weight, each person is over 99.7% human.
Oh. That's still bothering me. I also thought you were going to take it to like a universe analogy. Like
No.
No, it's just...
I can't tell you universe fun facts. You already know them.
Like I thought you were going to say like bacteria, like the amount of bacteria in your body is greater than the number of stars in the Milky Way or something like that. Oh, but it's just all here. We just brought it all the way back down to I am 90.
But those bacteria are all made of star stuff. So
bringing it back around. Nice.
So I think you still have to like them.
Wait, okay. What was the 56%?
Yeah. So you're, in terms of the number of cells, you're
The number of
56%
cells.
bacteria. But in terms of weight of cells, you're 99.7% human.
Okay. Well, I guess that's very telling that bacteria cells are very small, I
Yeah.
guess. But then also how symbiotic our bodies are, I guess,
Yeah.
that we're hosts to a lot of bacteria.
Yeah. So there's a concept in bio, not to nerd out on you in biology stuff, but there's a concept that I learned about in taking my plant morphology class that we're trying to stray away from thinking of singular organisms.
Mm.
This is very like on the edge of where bio is right now. And there's a concept called a holobiont, which is what we would consider an individual like human to be, that you couldn't live without the bacteria that are in your body. I mean, they're 50-some% of you. And so because you can't live without them, are you really one singular organism, or are you like a host to a bunch of organisms that help you be the organism that you are?
Cool.
And so a holobiont is what we call like an entity that like relies on other entities as like one organism, if that makes sense.
Is it hollow like HOLLOW?
HOLO.
Oh, okay.
Yeah.
I was like, whoa, am I also hollow?
No, definitely not. Yeah.
Very cool. Okay, I'm gonna give that a 9.
Okay.
Because I'm probably gonna worry about that a little bit for a while.
Yeah, a bad 9. I was about to say, after getting an immediate U, I was not expecting a high number, but... All right, this one's another bio one. It's the last bio one, but I figured you know enough about space. Time to bring you in a little to the bio stuff. So for our second fun fact, while there are size and structural differences, giraffes have the same number of cervical vertebrae, which are neck bones, as humans do.
Aw, well, I love giraffes. But yeah, that's pretty weird.
Yeah. We
They
each have
have-
7.
7?
Yep.
So they must be giant.
Yeah. And ours are very small.
Huh. But also, how do they have much mobility if they're just like giant blocks?
Well, that's part of the structural differences. Like they're not just the same exact ones that we have but bigger. There's like differences in how they're allowed to like move and stuff like that. So they're not like shaped the same but just bigger. They're like also differently shaped. But
Well, I love giraffes, so I give that fact an 8 because I'm not gonna worry about it after we leave.
yeah.
I
Awesome.
still appreciate it.
You're welcome. This one I feel like I saved the best for last, I think, because I think this one's very you. Like for some reason I saw this fact and I was like, Phoebe's gonna love this one. So you might already know it, but the temperature of the air in a lightning channel may reach as high as 50,000 degrees Fahrenheit, which is 5 times hotter than the surface of the sun.
That's awesome. Cool.
Yeah.
I did not know that. Lightning.
Yeah.
Do you know the lightning channel? So is that the whole bolt? Do you know what a lightning channel is?
I actually should have looked that up before I just like said it on a show that I'm supposed to like know what I'm talking about.
I'm
but
just curious now.
I would assume it's more about maybe like the radius of where they're measuring out to, because I imagine it's more
yeah.
probably about like maybe they're saying like at the hottest point, like whether that's the center or right around that, whatever gets to be the hottest. I would assume that.
Cool.
But
That makes me want to learn more about lightning now.
yeah.
I feel like I've learned more about stars than I've learned about lightning. Honestly.
Yeah.
But what's cool about we still have a lot to learn about our own sun too, because though the surface might be cooler than that, when you like leave the surface a little bit, it's like way hotter. It's way hotter than it should be.
Yeah.
I don't have numbers on me, but we're still trying to understand like what is this crazy jump in temperature once you leave the surface of the sun.
Yeah.
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 Mm.
But lightning has it beat on the surface. So
Lightning has it beat.
Yeah.
Yeah.
And I have one other thing if you're interested in lightning still.
Sure.
That this might be the part that maybe you would have already maybe known a little bit. But for our listeners maybe more so. That it's lightning's extreme heat that causes the rapid expansion of the air and the like accompanying shockwave that creates thunder.
Oh, cool.
So it's from like the same
cool
property. Yeah.
I also never thought about that
Yeah.
either. Yeah. That makes sense.
Isn't that awesome?
That's awesome.
Yeah.
Good facts. Good facts. And thank you
Yeah.
for bringing it back down to
Yeah, it's like it mentioned the sun. But yeah. How are we feeling? 0 to 10 on that one?
Oh, yes, I have to rate it. I forgot. I give that one a 10.
Okay.
Mm-hmm.
Only high numbers.
Mhm.
I can respect that. I've had zeros before. It's okay if you want.
Well, I didn't know any of the facts.
Okay.
And as you said at the beginning, we are both lovers of fun facts, so I was not going to rate any of them 0.
Aw. Awesome. Well, with that, we're actually going to take a short break. So stay tuned and we'll be right back. Welcome back to WFNP 88.7 The Edge, Rosendale. This is continuing with Curiosities of the Cosmos. I'm your host, Allyson Sheneman, and I'm joined by Phoebe Heretz, a senior and student of astronomy and physics at SUNY New Paltz. So for our last few minutes, and to end every episode, I ask the guests to bring in their favorite question that they've ever been asked. So Phoebe, what is your favorite question?
Thank you, Allyson. So I have a lot of experience talking to the public about astronomy at this point, and a whole range of ages as well. And I will say, I think my favorite questions I get asked are from little kids.
Yeah.
And they know a lot. They know surprisingly a lot about the universe, and they also have very uninhibited curiosity too, so they just ask everything. So when I was thinking about this question of what is my favorite question, I couldn't really come up with just one, because they're all great, and that's one of my favorite parts of being a science communicator is answering awesome questions. But I think my favorite category of questions are questions about the scale of the universe and being ready to just totally blow everyone's mind. So for example, like, if you think of the Earth as a peppercorn and the sun as a basketball, it's far away. Like, if in that scale, the Earth is almost 100 feet away from the sun.
Wow.
And so that's just telling that, like, the sun is incredibly bright and incredibly hot if it can warm us from that great distance away.
Yeah.
I love questions about how big is the universe. Really, really big. Unfathomably big. I guess going back to, like, the solar system analogy, though, like, the farthest thing that we humans have sent out into space are the Voyager crafts that left in the 70s, and they're going at 30+ thousand miles per hour, and they have only just left the heliopause, which is, like, the limit of the solar wind. And so they're technically in what we call interstellar space now. But even so, they've traveled 15 billion miles, which is a lot. That's very far. But at the same time, that's only like 2/10,000ths of a light year. And so when we think about the scales of the universe, we talk in light years, which is the distance light can travel in a year. And that's 5.9 trillion miles. So just this, thinking about just the scale of our solar system, the farthest thing that we've sent out, 2/10,000ths of a light year, and thinking that the entire observable universe is 13.8 billion light years across.
Yeah.
It's an unfathomably large place.
It's humbling.
Yeah, very humbling. And that's one of my favorite things to talk to the public about, is how incredibly big it is.
Yeah. Do you often find, like, especially with little kids, I feel like when I would do shows for, like, elementary groups and stuff, that I often get asked about, like, visiting other, like, solar systems. And I think maybe it's because I tailor a lot of my shows to talking about the solar system, talking about, like, extrasolar planets and, like, planets outside of our solar system. But I do get people that ask often, like, how likely is it that we will get there, and how soon is that something that we could expect to do? Do you find that you often also get those kinds of questions?
Yes, definitely.
Yeah.
And try to let them down easy.
Yeah.
Because unless we come up with new physics, I don't believe we're going to travel between stars and planets unless we take generations and generations of human lifetimes to do it.
Yeah.
Yeah.
Yeah. No. And I feel like a lot of people, rightly so, are like really impressed with some of the, incredible like engineering feats that happen, especially in astronomy, and how crazy it is that we can land spacecraft on other like solar system entities and stuff, or do past like flyby missions, and to have sent something even just to 10,000ths of a light year, the kind of like engineering feat that is. And I feel like a lot of people jump to like, well, then how close are we to this next crazy idea?
Which is good.
Yeah, it's a good thing, but like you said, it's tough to let people down easy with things like that, because I think some people think then, oh well, things have changed so much, things have gotten, like, we've learned so much in the last 50 to 100 years, like maybe it's something that'll happen in my lifetime, and that's always a tough one.
We can't rule it out. We can't rule it out. Wormholes might be true.
Yeah, and there are lots of things that we do now that we never thought were possible before.
Exactly.
Yeah.
So that's an important part of being a scientist to me as well, is remaining humble.
Yeah.
Because to say that we figured everything out about the universe is just not true. So
yeah,
remaining open, remaining humble, I think is really important.
Yeah. I think very inspirational to people who are starting the field, in order to have it like be presented in that way, where it's like not as it stands right now, but
exactly.
There were lots of things that we do now that we didn't think we could have done 50 to 100 years ago. And so to make it maybe like a passing the torch type deal, or passing the baton, to be like, well, we can't do it as it stands now, but maybe that's something worth your time. Yeah. Do you feel the same way with like scale of the universe and solar system stuff when you're talking to kids, to be like,
yeah. I think I love that reaction, especially about how big the solar system is, because we've only ever seen it like learning in elementary school. We see everything on like one piece of paper, like all the planets aren't to scale. Everything's way too close to each other. So then to talk about like the actual scale of the solar system, where if the Earth is a peppercorn, the sun's a basketball 100 feet away, Jupiter's 500 feet away, and then Pluto's almost a mile away.
That's
like
crazy.
we don't learn the solar system like that, and that's our home in the universe. So then from there it just becomes like unfathomably big.
Totally.
So I love presenting that to kids and to adults as well. I feel like many of us don't understand the true scale of things. It's awesome.
I think something that we talked briefly about before the show was about what it's like to make information that's really cool and like fascinating to us, not only like understandable and accessible, but still keep it interesting. And that's something I think, especially in doing planetarium shows, is a skill that we've really had to like hone. I know for me it was a struggle at the beginning to figure out like, how can I talk about the things that I'm really, really interested in, I think are so exciting, but they're so like at the forefront of what science is doing right now. And I feel like most people got through like high school science and then never touched it again, and probably didn't even like it when it was first presented to them. And so I feel like trying to make it like understandable and like at a level that people can really access and feel like it's easy for them, but also keeping it really like fun and engaging, is a really hard thing to balance.
It is hard.
Yeah.
It's really hard. And especially as science communicators, talking to different age groups as well, because then you have to change the story or how you tell the story depending on what a third grader versus an adult can understand. So it's let alone talking about research to people that aren't scientists, but it's also in different levels of understanding and ages. So it's really challenging in that way. It's like multi-layered challenge.
Yeah.
But it's so important though, and it's gonna be important to me for this whole career. It's one of the reasons why I entered this career, was to make science exciting to everybody. So I accept the challenge.
And I think by having, especially when you're talking about like scale questions and things like that, having those examples of like things that become more tangible.
Exactly.
If that makes any sense. And instead of just being like, yeah, it's this many miles away, or it's this many light years away, in a way that you're like, yeah, that's a big number, but that makes no like physical sense to me.
Right.
To be able to say like, think about things that you know and you could touch and you can feel, and now separate them by this much.
Yes.
And you just picture it bigger. Like, I don't know. I think those are really important, like those types of like analogies, I guess, to making science more accessible.
Yes, I think that's one of the best ways.
Yeah.
But that reminded me, so the solar system model at Cornell.
Yes.
That our sun is in Ithaca, New York, but then the closest star to us would be in Hawaii. Was that the?
Yeah.
So that's another level up on the scale.
Yeah.
Crazy.
It is crazy. And I mean I don't remember the exact like size that the sun is in that scale,
but about basketball, if not a little bigger.
Yeah.
But like similar.
That, or like a grapefruit, something along those lines. Yeah.
Same.
Small enough.
Type of scale, yeah.
Yeah. No, it is crazy.
That's wild.
And all of the, in that scale, however small the sun was, all of the planets and stuff fit in Ithaca. So like while I was there for my REU, like we walked the path, like there's a guided tour or whatever that you can take. And I mean, it's not a short walk, but it's not a long walk either. I mean, it's like a mile maybe. Mm-hmm. And you start like in the center of Ithaca and you just kind of walk to like one of the near edges of it. And so to think like, well, all of the planets, like you get a sense too of like, oh, these ones are all kind of like right back to back.
Right. The inner rocky planets. Yeah, they're all fairly close to each other. Yeah,
because from standing at the sun there, you can see the next, I think maybe it's just 3, and then Mars is a little farther. But you can get a sense of like, oh, these ones are all really close. And then all of a sudden you're walking a mile to get to Uranus and Neptune.
Yeah.
But I think especially that scale, like what you're saying, is like sizing it out of just the solar system, which is already crazy big enough, and then adding in neighboring stars, and then thinking about like what that means for other galaxies, and thinking about like the edge of, quote unquote, edge of the universe, our like observable edge to the universe. It's like, yeah.
It's impossible, but we try.
Yeah. I think it's one of those that feels like so challenging, but in such a rewarding way, because once you do have your like tangible examples to kind of like grasp onto, it makes it feel like the impossible is like not that impossible.
Or I just love the perspective that it brings back to home, that we are in this big mysterious place, but we here on Earth have this precious planet that, despite it flying through the void, is a perfect place for us. And that is one of the things that I love about communicating the universe too, is how awesome it makes Earth look, and how important it is to take care of it and to take care of each other. Yeah, there's, I think it's a T.S. Eliot poem, if I'm not mistaken, where he says like something about, I'm gonna butcher it, so, and everybody else can just like Google it at home, and I'm like here trying to come up with random things. He says like and we will have journeyed out with the most important
only to find that the most important journey was like coming back home. It's something along those lines.
Yeah.
I think in your experience working in like renewable and like sustainable fields and like trying to, because you were a sustainability ambassador on campus, right?
Yes.
And so trying to like keep that still at the forefront, to like having, I don't know, that those two fields and concepts, just like sustainability in general and on like an earth scale, and astronomy feel like such compatible fields, I guess.
They are, yeah. Totally compatible. I sometimes think about, though, should I have gone straight into climate science? And because that's still an important mission to me, is the sustainability of the earth and fighting the climate crisis. And so I feel like, though, that I approached it in a more indirect way than I could have by studying astronomy, because I feel like the perspective is the same.
Yeah.
When you study astronomy, you see how fragile the earth is. But at the same time, I feel there's value in being able to successfully communicate that to people, and I feel like astronomy is a good avenue for that. But at the same time, I feel like I could have pursued a more direct avenue and studied climate science. So I do think about that, and I keep that work as part of my life, both in my job, and I just joined the United Nations Association and trying to promote the sustainable development goals and everything like that. So it'll be a part of my life, but I do think about that. Like, should I have just gone straight to it and like figured out the next great carbon capture idea or something? I don't know.
I think that like you're just the kind of person that like goes after what you want and like makes it work, if that makes any sense.
Oh, thank you.
So I feel like in the same way that I was hearing in you like recounting your like life kind of story of like how you got to where you are now, that those moments that you had where you were like, wow, this was really meant to be, like this like shouldn't have or couldn't have gone any other way, like this is just so perfect, that I think regardless of what you would have picked, you would have found those moments and like found a way to be fulfilled in that way.
Thank you.
And I think there's totally still space within within astronomy to lean into that too, because I think something we talk a lot about in my biology classes here especially is the need for scientists in legislation decisions and in government and informing legislation. And so I think that I can't imagine that there's not a part of your future that involves some kind of activism, I guess, in that way. Yeah.
Thank you. We'll see.
Yeah.
Yeah. It'll be a part of my life, definitely.
Yeah. Well, with that being said, that does bring us to the end of our hour. So sadly, that's all the time we had for today. I know. So thank you again, Phoebe, for coming on the show. And of course, thank all of you for listening. This has been your host, Allyson Sheneman, and my guest,
Phoebe Heretz,
on Curiosities of the Cosmos.
Thank you.